Our solar system is a very diverse place. We have places with temperatures high enough to melt lead, to those with temperatures so cold that gases commonly found on Earth, like nitrogen, are frozen solid. We have moons that are smooth as ice, and those with canyons far deeper than any found on Earth. With all of this diversity, we also find several commonalities. These give us important clues to how our solar system formed. Ahead, we'll take a look at those similarities and use them to draw comparisons between the planets and the moons, both in our own solar system, as well as other extraterrestrial solar systems. Stay tuned. It's hard to imagine, with all of the differences in our solar system, that there are some commonalities that we can discuss. The first commonality is that all of the planets lie in the Sun's equatorial plane. We call this plane the ecliptic, and it's easily visible from this animation. The notable exceptions to this rule are Mercury, with an inclination of 7 degrees, and Pluto, with an inclination of 17 degrees. We can easily observe this relationship by looking at how the planets and the moon line up in our sky at night. Use your eyes to form the line between each of the planets here, and it will create for you a line defining the ecliptic. All planets revolve in a prograde direction around the Sun. So a couple of terms here. Revolving is the same concept as orbiting. Prograde is a word that describes something moving in the same direction as the Earth. So in other words, all of the planets revolve in the same direction as the Earth does. That direction is counterclockwise as viewed from above. Likewise, most planets rotate or spin on their axis in a counterclockwise direction as well. Now there are a few exceptions to this rule: Venus, Uranus, and Pluto. I will note here that it's possible that even these planets, the exceptions to this rule, formed rotating in the counterclockwise direction, and that something catastrophic changed their direction at some point during their history. All planets move in circular orbits around the Sun. There are 2 slight exceptions to this rule: our friend Mercury, and of course, Pluto. Both of these have eccentricities of about 0.2. So I'll remind you, when we discussed Kepler's laws, that point 2 is still reasonably circular. So there aren't any extreme examples of eccentricity in our solar system, at least as it applies to planets. Also, moons orbit their planet in the same direction as the planet rotates. If the planet rotates in a counterclockwise direction, its moon also orbits in the counterclockwise direction. So watch this animation again, paying particular attention to the moons orbiting around the planet. Note that there are a few examples where this is not the case, but this is pretty rare, at least within our own solar system. Moons also orbit very close to the equatorial plane of their parent planet. In this image, you see the slight inclination of the moon's orbit around Earth. At only 5 degrees, this inclination is still considered negligible. Additionally, in a manner similar to the planets in our solar system, most of the moons also orbit their parent planet in circular orbits. All planets have atmospheres. The only notable exception is Mercury. Now I will point out that not all of the atmospheres are extensive, but all have permanent atmospheres, at least to some extent. In this image, you can see a very thin atmosphere pictured as a blue glow in this backlit image. It's interesting to note that the Earth's atmosphere is also very thin like this. If we were to reduce the Earth to the scale of a basketball, the Earth's atmosphere would be about the same thickness as a sheet of ordinary paper. So even though it's thin, that doesn't mean that it can't sustain or support life. There are additional similarities if we categorize the planets in 2 groups. terrestrial planets, or Earth-like, and Jovian planets, or Jupiter-like. The terrestrial planets pictured here include Mercury, Venus, Earth, and Mars. In contrast, we can name the Jovian planets. The Jovians consist of Jupiter, Saturn, Uranus, and Neptune. Notice that Pluto is suspiciously missing from both the terrestrial and the Jovian planets. This is not because Pluto was demoted from planetary status. It's because Pluto actually shares characteristics from both groups. Another interesting situation is shown by this table. We go from increasing distance from the top to the bottom. Notice the gap in between any two planets grows distinctively larger. The terrestrial planets, then, are very close to the Sun and are relatively closely spaced compared to the more distant and widely spaced Jovian planets. Now, we can compare the characteristics from the Jovians to those of the terrestrial planets. So while the terrestrial planets are all close to the Sun, the Jovians are all very distant. This is important because we don't see any gaseous planets close to the Sun. Terrestrial planets' orbits are closely spaced, whereas they are widely spaced by Jovians. Now think about this just for a moment. It kind of makes sense. The Jovian planets are very large and very massive. That means that they have a gravitational effect on the other planets. So we would expect the bigger the planet, the wider the gap in between them. Terrestrial planets have small masses compared to Jovians, small radius of the terrestrials compared to the Jovians. The terrestrial planets are rocky, the Jovians are gaseous. The Jovian planets have no solid surface. That tells us that the Jovian planets have a very low density, and in fact that is the case, with densities near that of liquid water. Terrestrial planets rotate very slowly. The Jovian planets have very rapid rotation. Jovian planets have very strong magnetic fields, and in comparison they have a large number of moons, and all of the Jovian planets have planetary ring systems. In closing, the difference between the two types is a bit more evident when considering a concept called the frost line. The frost line marks the distance from the Sun where it is cold enough for hydrogen compounds to condense into solid ice grain. These are common in the Jovian planets, but these same elements exist only as gases in the terrestrial planets. So that's it for the similarities that we find in our solar system. We will be spending a lot more time talking about the differences. More to come on that. It is also important to note that we'll look for these same similarities, and of course the differences, as we start to look at other planetary systems around other stars much later in the course. Thanks for joining.
North side's all clear.
Great, let's look at some planets.
Hey, why'd you lug your telescope all the way over here? Leonard has one in our apartment.
Yeah, I'm gonna use Leonard's. Might as well hold my hand up like this and squint.
I don't know, it seemed pretty good. You know, once when the cable went out, I watched an entire episode of The Bachelor on a TV across the street.
This one's more of a professional model.
So was the girl he picked?
This baby's got a 10-inch diameter with f10 ACF optics.
And tonight, Mercury is at its highest elongation.
It makes faraway things seem close, and Mercury is a planet.
I know Mercury is a planet, but the other thing was helpful.
Oh,